Yeah. Yeah. Thanks for the introduction and welcome. I repeat a motivation from one of the talks earlier this day. You all probably know this. Why use multiple GPUs? Yeah. Sometimes you just need to compute faster because you need to match a quality of service requirement, like in weather prediction, where you should be faster than real time, otherwise you're not predicting the future. Or you just need to compute larger LLM models, more higher resolution CFD models. So as Mats has shown this morning, there's the data is going to explode, so you really need multiple GPUs to really put that data into reasonable action. So to repeat, this is a part of a 3-part series and presenting the multi-GPU programming landscape on this semi-scientifically axis with, on the x-axis, the generality, so how domain-specific is it, how general can I express the algorithms, and on the y-axis, the productivity. You can probably argue a lot where to exactly put these dots. I think we found a way that someone will always disagree and some will always agree. So at 8 a.m. this morning, Mats gave an introduction to the high-level libraries that really abstract most of the work away from you so that you have really the most productive experience. And if your operation is directly available, it can also be extremely performant. Then just before this, Manolis talked about the task-based runtimes that are used to build the higher-level runtimes Mats has introduced before. And now I'm going down in the productivity and up in the generality, talking about the advanced multi-GPU scaling with communication libraries. So what's used by all of this to actually carry out the data movement needed when you program multiple GPUs. So yeah, as I said, what will this talk be about? If you have multiple GPUs working on one problem cooperatively, at one point you need to exchange data so that they stay in sync and really solve the same problem and do this productively. So that is what this is about. How can NCCL, MPI, NVSHMEM help you to efficiently orchestrate that and compose it with GPU communication? All the models here are CUDA-aware, meaning, as you see from the arrow, they can directly work with GPU memory, so directly move data from GPU memory to GPU memory across the most efficient data path. High level with MPI, two-sided communication part of the API looks like the MPI that has the rank that has the data, which in this case is 0, calls MPI send on the array in GPU memory, and the GPU that accepts the data calls receive. With NCCL, this looks very similar. It's also a send-receive, two-sided communication pattern. Important difference here is that you see the stream argument last. So it is a blocking operation with respect to the GPU stream, with respect to the GPU. So in the stream, it's executed in, but it's non-blocking with respect to the host. So right after these calls are dispatched, the CPU is free to do other work, schedule more kernels, and so on. And last but not least, NVSHMEM, which most note as NCCL. It's also, this is the host API. I also go to the device API later. This also has a stream, so it's non-blocking with respect to the CPU. And also you see that there's only one part. It's a one-sided communication model. So as I go into more details later, this is enabled with a symmetric heap. Okay, what do all of these and the programming models have in common? Because they are multi-node, multi-GPU programming models, you need a bit of help launching them. So it's not like you just launch your executable and the executable can have everything in there to make sure that you launch one process per GPU, which is the typical method thing. So you take usually a launcher, which in case of a Slurm cluster is typically srun, but also the programming models typically come with a launcher like MPI run or NVSHMEM run. These have a lot of options to map your processes correctly on your resources. Here, from simplicity, I'm just showing the most important one. How many instances do you have? So if you use that launcher, provide your app with your arguments, it takes care of distributing, launching one instance of your application for every GPU, and after the library is initialized, they get back rank in case of MPI and nickel, or processing element PE ID from 0 to number of processes -1, so that they can safe identify themselves, know how many others are there, and then can use that to orchestrate their communication. Okay, let's get started with the first programming model, MPI, which stands for Message Passing Interface. It's a long-established standard to exchange data between processes via messages, and for that it defines an API for point-to-point communication. You have already seen the MPI, send, receive, but also a rich set of collectives, reduce, all reduce, and so on. There are many implementations with bindings for probably every language you care about. I just list a few here, open source and commercial. Step back, a bit of foundational technology, which is used to either enable all of the libraries or required even for their functionality or speed their functionality up. The most important fundamental building block for CUDA-aware MPI is unified virtual addressing, which we introduced way back with Compute Capability 2.0. And what this does is when you allocate any memory in a CUDA program, the pointer is part of this unified virtual addressing, not to be confused with unified memory. So range, so that you can identify from the virtual address of a pointer its physical location. You can query the CUDA driver, where does this pointer live? And that allows a library like MPI to become CUDA aware, because I can just pass in a pointer, the library can query, is it a CPU pointer, a GPU pointer, on which GPU, and then can take the right steps to efficiently move your data. So that's the enabling technology. But there are two others I want to touch on. One is part of the GPU Direct family. One is for peer-to-peer transfers, which allows data to be moved directly from one GPU to another GPU in the same node via PCI Express, or if available, NVLink, which you have probably heard earlier. NVLink also is multi-node capable, so which gives, of course, much higher bandwidth, because you can use the high bandwidth NVLink connection between GPUs and avoid any bottlenecks of intermediate staging in CPU memory and so on. Then there is GPU Direct support for RDMA, which allows third-party PCI Express devices to directly read and write to and from GPU memory. So in case of an InfiniBand network adapter, it can directly read data from CPU memory and send it over the network to the destination, so that you avoid also any intermediate steps for potentially harming performance. So let's take a look at a very simple example with CUDA-aware MPI, how this is put into action, so that you can contrast that and better reason about performance. I'm looking at MPI rank 0 doing an MPI send from a GPU buffer, MPI rank 1 doing an MPI receive, matching that send to a GPU buffer to show how CUDA plus MPI works in principle. This is looking at 2 GPUs in 2 nodes. So depending on your MPI implementation, your message size, system setup, you probably see something different, but I think this is still a very useful mental model to reason about performance and what can potentially happen within a communication library like CUDA-aware MPI. Okay, let's first start with the best case. We have support for GPU Direct RDMA and a network supporting that. We just pass in our device buffers into the send receive calls, and the library will directly move data over the PCI Express Plus network and so on. You can also see that when you run it with Nsight systems and profile it to check what's really happening. And the most relevant part here is what you're not seeing. You're not seeing any GPU activity, you're not seeing any CUDA API calls, and that is because all the transfers mastered by the network adapter. What you see, however, is, that's why I've enabled the GPU matrix sampling, you see activity on the PCI Express bus. That is the network adapter reading data from GPU memory or writing data from GPU, depending on if you're receiving or sending data. So that's very efficient. If you're, for whatever reason, GPU Direct can't be used because of the node topology, system setup issues or so, you can still use device pointers, and MPI will take care of staging, doing the necessary staging, which then involves potentially involving 2 buffers on the CPU, but it will all nicely pipeline that, which you can also see from the Inside Systems timeline, that you have this multiple chunks of device-to-host transfers, and actually the network transfers run pipelined with that, so that you still get reasonable or good performance depending on the exact constraints. So to contrast that, what would you need to do if you don't have a CUDA-aware MPI? Then you first need to call a CUDA-mem copy, device to host, wait for that to finish, then you can call your CPU MPI, wait for that to finish, and then you can copy the, need to call CUDA-mem copy to copy device host to device again. Aside that this has far more steps, it also has a big downside that it stalls the pipeline after the CUDA-mem copy and after MPI, which you can also see if you look at this in Inside Systems. You have one large copy, and then need to wait for that, and there's no overlap at all between network and host to device copies. Yeah, if we take the OSU benchmarks we just looked at, and I've taken a system that's available for scientists for some comparisons, Joules Booster in Jülich, and have run this benchmark with a sweep of, with the default sweep of sizes, and compared CUDA-aware MPI with GPU Direct RDMA, the green line. You see that this saturates the network bandwidth of the HDR200 InfiniBand network. With CUDA-aware MPI, you lose some performance, but it's still good. With staging, you're really harming your performance. So you want to use a CUDA-aware MPI and make sure your system is configured correctly. If we go intra-node, where we can also use NVLink, the differences, of course, amplify significantly because the delta, performance delta between PCI Express and NVLink is just much higher because PCI Express matches network bandwidth, but not the NVLink bandwidth. And therefore, there it's even more, providing more benefit, GPU Direct. Okay, so does it also translate to real application performance? And yeah, it does. What I've taken here is as a CUDA-aware application use case is ICON, which is the icosahedral non-hydrostatic model for which is used for numerical weather prediction in climate and climate simulations. It's developed in Germany and Switzerland, and it's used in operational weather service in both countries as well in multiple other occasions. For this benchmark, we use the cubic workload at a 10-kilometer horizontal resolution with 190 vertical layers, which is a typical setup. And what you see here from the screenshots is that compared to a CPU MPI, the CUDA-aware MPI for ICON avoids unpipelined transfers. So here you see the CPU MPI, you see the host-to-device copy, then a long gap with no GPU activity, and then the host-to-device copy again after MPI is completed. And when we look at the CPU version, in this case, a profile of running on a single node so that we can see the peer-to-peer transfers, you see that the host-to-device copies are missing, and that you get peer-to-peer transfers. And as you can see also from the highline, you see that the overall timeline is much denser with much less gaps. So execution is more efficient. If we run a scaling experiments comparing these two, we see a 1.4x speed up for the scale really relevant in production, which is the about 8 to 12 nodes. And we also have done an academic exercise to scale out. So at 32 nodes, we even see a benefit of 1.2x, 1.6x for the on the EOS supercomputer with DGX, which H100 GPUs and an NDR400 network. Okay, let's switch gears and go to NCCL, the NVIDIA Collective Communications Library. It's a library for efficient communication with GPUs. It started off with collectives, for example, all-reduce, as are required for data parallel deep learning. Since version 2.8, it also supports send-receives between GPUs, which allows to, besides the effectively to express arbitrary communication patterns, including all-to-all, all-to-all-V, and so on. Compared to MPI, this is a library running on GPUs with any GPU accessible data. So the communication calls are translated to GPU kernels running on streams, as I have already said, which makes them blocking to the GPU stream you have submitted them to, but non-blocking with respect to the host, which enables to avoid some CPU-GPU communication, and especially for collectives, allows to leverage the compute throughput to really run collectives at the maximum speed. So I would, if you're more interested in NCCL, I would strongly recommend you to watch the recording of my colleague's talk, Sylvain Jagot. He has presented this on Monday, latest news on NCCL. And one slide he had here is showing the collective communication bandwidth achieved with the latest version of NCCL across generations. And as you see, there are really high bandwidths achievable if especially NVLink and Sharp can be used, both internode, multi-GPU, and multi-node. So aside from there's the high collective performance and the benefit of avoiding synchronizations. I wanted to demonstrate that with a source code. I will have a larger link on the last slide, just in case you look at the slides that's on the bottom. It's a bit simplified version from an example code available on GitHub. On the left, you have the MPI version, where you see that you need to synchronize the compute kernel because before you can start communicating, start issuing the communication for the data that that compute kernel has produced. Compared to that, NCCL looks very similar regarding the send-receive, but you can avoid the CUDA stream synchronize because the communication is submitted in the same stream as the compute kernel. So it doesn't start before the compute kernel has finished, but you can already enqueue the work, and the CPU can go out to do other work, which allows to more eagerly schedule stuff to the GPU and makes the timeline generally denser. Here, I've also taken a NCCL application use case. Of course, there are, I mean, if you go around the conferences, almost every deep learning application uses NCCL. So I wanted to get something potentially new to this audience, which is VASP, the Vienna Ab Initio simulation package, which is a very versatile package to do ab initio calculations based on first principle molecular dynamics, which is, for example, used in material research. And that has started off with CUDA-aware MPI, but later on added a NCCL communication option, and that leverages multiple things. One thing is higher performance because of GPU-accelerated collectives. Because of the CUDA stream-aware interface, it minimizes CPU-GPU synchronization. And as a follow-on, the asynchronous GPU execution made it easier to express communication computation overlap. Therefore, in the NCCL version, communication computations overlap is implemented. It was, but not in the MPI version. So the comparison I'm going to share is not 100% fair. MPI could be better if work would be implemented there, but still, it is a side effect of making it easier, at least in this code. Here I'm comparing, also you see that on the left side it's a CUDA-aware MPI. You see a lot of white space and everything is serial. And on the right side you see the NCCL version where you see kernels in 2 rows. So the communication NCCL kernels are overlapping with compute kernels. The GPU is busy all the time. It's what I'm highlighting here is actually a reduced kernel. So that's the reason why there's white space on the left side, because it's a reduction is done on the CPU and not with an efficient nickel kernel. If we take the hafnium simulation with 216 atoms and scale that also on EOS from 4 to 32 nodes, at the limit we see a 2.6x speed up due to using nickel instead of CUDA-aware MPI. At the bottom there's a link to a blog post which provides more information on the exact use case and how this is done. Okay, then let's switch to NVSHMEM, which is an implementation of the OpenSHMEM standard and which builds on the partition global address space, meaning the core principle is that all the arrays we work with for communication are allocated from a symmetric heap. So they need to, if something needs to communicate it needs to be allocated with NVSHMEM malloc to be accessible. And that NVSHMEM malloc makes sure that the memory is properly aligned, registered with the network adapter for inter-process communication over NVLink, and so on and so forth, so that it enables the one-sided communication. This is a collective call, so you need to really call it with the same sizes on every process, and therefore it's also called a symmetric heap. So if you do an allocation, you get the same sized allocation, same sized chunk on each GPU, which has the benefit that it avoids communication to communicate offsets and so on, because you just know, okay, my peer I will need to send this data to has this an offset X, and you don't need to reason. You can do this computation locally. You don't need to ask your peer, like in a two-sided model, where should I put this data? You can just go ahead and use, write the data directly where the peer will need it next. It has a CPU API in the blocking variant and a stream ordered variant, which I've shown on the first slide, but also, very importantly, CUDA kernel interfaces to read data with get operations, write data with put operations, atomics to synchronize, and some memory consistency APIs. Big benefit, the memory, on the point of the memory consistency, these give you exactly the control where you need to wait for things to complete, which also limits the amount of synchronization between processes needed. Oh, I missed to mention that actually for nickel. All these programming models are fully interoperable. So you can use nickel in an MPI program. You can use NVSHMEM in an MPI program in case you have a legacy code base and want to accelerate that. Okay, so what's the thing with device-initiated communication? If we have a SHMEM program with CPU-initiated communication, typically, we do the compute on the GPU, and the communication is issued from the CPU. So you need to synchronize at the boundaries, as you have seen. So you start your kernel, wait for that, then you do your SHMEM put, wait for that to finish, start the next iteration. So very commonly used, similar to MPI. Problem is that the offload latencies to launch the kernel synchronize data on the critical path, and you don't get overlap between communication and computation. With that model, you can express communication and computation. I have examples of that in the source code. I will provide you the link on the last slide. But it makes the code more complicated, and also you have a lot of API calls added. Compared to that, GPU-initiated communication does both compute on the GPU and the communication on the GPU. So you can start sending out data as soon as it's computed. That benefit is clearly you need to launch less kernels and less operations, so less offload latencies. You get on the GPUs, you get natural communication computation overlap just by threading, the same technique you use to hide your global memory access latencies, just have multiple threads run on the same SM. And for some algorithms, it can be easier to express them with inline communication. So how does that look like in code? Thread level communication, so that every thread just does a single element put here, which is very fine-grained, so you get the maximum overlap between communication and computation with threading. And it's a very efficient mapping on NVLink fabrics, like we have them on DGX systems. And yeah, you just, instead of doing a load store, you just call NVSHMEM float p on the data you want to send this to, the source data, and then the destination processing element where you want to put that. There are also APIs to form larger groups, which are necessary for networks like InfiniBand, which don't have that high message rates like you can achieve over a memory fabric like NVLink. You still get overlap between warp and blocks, but you form larger messages so that the network-like operations can work more efficiently. So this is one benefit, but really what's can put your code to the next level is that kernel initiation communication also allows you to avoid certain kernel boundaries, so you can fuse kernels to keep more state into registered or shared memory and avoid whole memory round trips to just store them to global memory to have a separate communication kernel and then reload them. And this sometimes requires in-kernel synchronization, and that is also possible by device-initiated communication if you launch your kernel in the right way. So you can really move the whole iteration loop into your kernel. In this case, it's a simple one, relatively. In your case, it's mostly probably not so much the whole iteration loop, but rather two kernels that you no longer need to launch separately because they have communication in between, but things you can do together. Okay, here I also have an application use case, also from the HPC, QUDA, and we are looking at strong scaling the Wilson D/ operator. QUDA stands for QCD on CUDA. It's an open source library to provide building blocks for the necessary calculations in lattice QCD simulations on graphics processing units. It leverages device-initiated communication by NVSHMEM to overcome latency barriers when strong scaling. There had been most of the details are luckily quite stable, so you can take this GTC 2020 talk from my colleague for more details of what is following. What this does is, as I said, mostly overcoming the latency barriers by the need of launching many operations. So in CUDA, when you need to communicate, when communication happens, you first need to pack that data, communicate it, compute, because you want to overlap communication and computation. You have a separate kernel for the interior and the exterior. So if you look at the profile of a single node execution of CUDA, with MPI, you see that you have the packing kernel, the interior kernel, and the data copies. And the thing is that you see there are gaps between them, which are caused because it just takes too long to launch these small kernels, and that the communication takes longer than the interior kernel. And that is also not because the communication is not fast enough itself. It just takes too long to launch the individual copies. So, because if you would just put all the peer-to-peer copies together, they would comfortably run faster than the interior. Compared to that, with NVSHMEM, and we can build a fully fused kernel, so we don't just launch one kernel. Launching of the kernels can also run ahead for the next iteration. So we already, while the current kernel is running, we have already launched and provided everything to the GPU for the next one, which avoids all the white space on the GPU and also translate to a huge performance speed up if you scale out. This one is a relatively busy slide. We look at, again, EOS with DGX H100, 400 gigabit NDR, the given problems, and we're strong scaling the given problem size up to 512 GPUs. We look here at 3 different precisions in MPI and NVSHMEM. The differences is largest with the lower precision because there we do less compute, so relatively speaking, the communication is more important. And if we zoom into that, the thing we see that the further we scale out, the larger the performance difference is. So with NVSHMEM, although it really starts to get questionable if you want to throw more resources, but you can still get more performance if you go from 256 to 512 GPUs, where you see an up to 1.7x speed up over MPI. You also see that MPI doesn't really scale. The bump from 128 to 256 is strongly related to being the need launch multiple kernels, because at that point a partition change happens, which requires the MPI version to launch more boundary kernels. Okay, with that, I'm ready to conclude. There's a link for the where you can find the other CUDA developer sessions on this conference. Some will still appear, but most of them already happened, so you can watch the recording. I want to put in a shameless plug for CWE later today at 3 p.m., where you can find me and other colleagues from the GPU Comms team to answer your questions on MPI, Nickel, NVSHMEM, GPU Direct, and so on and so forth. I also want to advertise a talk with a very similar title I have presented last year, Multi-GPU Programming for Models for HPC and AI, where I also cover MPI, Nickel, and NVSHMEM. But there I'm using the linked multi-GPU programming model source code as a hello world to really go step by step on how does it look in source code with a single example, how do I express communication computation models in different variants, and and compare the performance of those. So yeah, you can find the example on GitHub and on NVIDIA On Demand, the recording from last year. So summarizing the different models for GPU Direct, peer-to-peer and RDMA. For MPI and Nickel, they improve performance if they are leveraged, but they both will also work if they are not available, because the libraries internally can do staging. For NVSHMEM, they are required because the one-sided model requires that mappings are set up so that I can really do something without involving the source or destination of the data. MPI, Nickel and NVSHMEM are CUDA stream aware, and can also work with CUDA graphs, so you can capture the communication in the graph to further reduce API overheads. Kernel-initiated communication is, as of today, supported with NVSHMEM, but coming soon to Nickel, as was shared in the Nickel talk on Monday. And yeah, the supported communication models are collectives. Call stands for collectives, 2S for two-sided, 1S for one-sided, and you see that MPI and Nickel soon will support all three, and NVSHMEM support collectives and one-sided. With that, I'm happy to take your questions.
Way in the back.
Thank you for talk. Nice talk. So one clarification. So NVIDIA also has this another package, Docker GPU NetIO. Where would that fit in this table?
It's not. So the NetIO is, I would describe as a lower level library that's used by frameworks like Ariel and so on, but not so much by HPC applications running on large clusters. So more it would not really fit in this this table. It targets a different use case. So edge computing, for example, when you need to directly stream data to instruments, that becomes relevant.
So the GPU's initiated communication that you showed, right?
Yeah.
Isn't it similar to that?
Yes. There's a lot of overlap in the technology stack, but it's just meant designed for a different use case, edge computing use cases, and the most prominent example being Ariel.
Okay, thank you.
Yeah.
Any other questions?
Just Jensen's keynotes on the Dynamo for the operating system. Do you think that those solutions that you put in here will be part of that Dynamo solution that will make it automatic in the future?
It's on the inference side.
I mean, any multi-GPU application needs to communicate data to use them together. And sure, these are building blocks that we build upon to build anything high level. That's it.
Just wanted to understand how you can use MPI and Nickel together. For example, I saw one use case in which you do, like for LLM inference, if you have like a prefill and a decoding like you have groups of GPUs doing something, and then the other group doing the decoding part. So I saw some code where you have MPI with nickel. Like, I don't know, when should we use just nickel purely, or like how do you make that kind of call? Like, how do you start with the code? Like, you should just use MPI first and then introduce nickel inside. Like, what is the best way to see, like basically start with the basic code which runs and then keep on optimizing? I just wanted to know some.
Yeah. So so the primary, as I would say, the primary reason to combine MPI and nickel is that you have already an MPI code. And then you can use nickel in the performance critical parts. So it doesn't. So the interoperability is important, that if you already have MPI, you don't need to rewrite your whole code in nickel. You just apply where it provides the most value, and the non-performance critical parts, you don't need to touch that. So therefore, it's more a question is, if nickel provides what you need, use that. There, I think I would say.
So if I write from scratch, I should just write in nickel directly?
Yeah.
Okay. Yeah.
MPI might be helpful for you to do the bootstrapping necessary to get this up. That might be a good choice, but there might also be other choices. But there's no reason to. You can, if the data is on the GPU all the time. I mean, obviously, if you have mixed CPU-GPU communication, then it might make sense to look at MPI as well. But generally, if nickel provides. You're running on GPU data, just start with nickel. And
from the communications library standpoint, are there concerns using them on a network which uses IPv6 addressing versus v4? Is the intelligence or differentiation between v4, v6 part of the communication libraries, or is that handled by the transport layer underneath within them? UCS
it's sufficiently abstracted away so that that's not visible. I mean, what's for performance very relevant if you're running on Ethernet, if that Ethernet supports RoCE capabilities, so that you get RDMA over Ethernet. But I'm not that low-level person. I think that's orthogonal to IPv6 and IPv4. So that's.
So the libraries are totally abstracted from
yes,
the.
That's not. I've never heard that this happens. This plays a role.
Have you had cases from your other colleagues or other people who have used these libraries over a network, Ethernet network, supporting RoCE, but the addressing scheme being IPv6?
I don't know. Please come to connect with the experts.
Okay.
Maybe we can help you there.
Sure. Thanks.
A quick question on footnote 1. Do you have any sense if MPI is going to add this extra parameter to their send and receive so that you can have the stream-aware
actually, the
communication?
person who is running that work group will be at the CWE, so I think better to just come there and discuss it there. Thanks.
Is there a native nickel launcher then? Because everything I've done has been MPI run of applications using nickel as the communication framework. But can you do nickel basically without MPI run completely?
And you need something to bootstrap the nickel communicator. That doesn't need to be MPI run. You can also use Slurm and then use other communication libraries, but it's not like you need something to bootstrap.
Okay, but nickel does not have its own launcher.
No.
Okay,
No.
thank you.
Yeah.
A bit of a naive question. Is there a CUDA-aware MPI for Windows?
Sorry.
Is there a CUDA-aware MPI for Windows?
I'm not sure. I'm sorry. I can't confirm, but I also can't deny because I haven't done the research on that.
Thanks for the great talk. So on Monday, I attend this very great nickel talk. So there, I think Selvin mentioned about the nickel's new feature called the symmetrical memory.
Yeah.
So I'm just wondering what is the difference between that technique and the NVSHMEM design?
So at a very high abstraction level, it's really symmetric memory. It's exactly the same concept of symmetric memory.
Yeah, please come here.
There are some differences. There will be some differences in how it's implemented because the way we built we're planning to build the Nickel device initiator is clearly focused on the needs of deep learning applications. So there are different trade-offs to make compared to NVSHMEM, but from the mental model as a developer, symmetric memory is exactly the same. So it will be one-sided communications with put, gets, and
I see.
Yeah. So the APIs will look different, and will need to do some different thing. But it's at a sufficiently high abstraction level, you can think about this equivalent.
Got it.
I would say.
And do you know if there is any side effects when using NVSHMEM or like the symmetrical memory feature when we have a very large computing scale? Because previously when we use some experiences that when we use OpenSHMEM and you trying to expand to a lot of GPUs, for example, or CPUs, there are some issues there.
I think that if you can best come to the CWE, and then we can look into that in detail.
Okay,
it's
Thank
a bit
you.
difficult to
Thank you.
answer.
Great. Thank you very much,
just in a
everyone.
short
That was the last
answer.
question.
Yeah.
But you can talk to Jiri outside of the room. We have to vacate the room for the next session. We really appreciate your attendance, and thank you very much.